artificial intelligence advancements in the field of myoelectric prosthetics have led to development of hands with multiple degrees of freedom. The anthropomorphic hand used in this video uses servos rather than DC motors. In this prototype proved to be a viable option when controlling finger kinematics. Servos are lighter than DC motors and are more precise due to their continuous rotation mechanisms. DC motors are more commonly used in prosthetics, even though servos demonstrate a higher degree of accuracy through proper control of angular displacement. With the use of servo motors, the time variable is eliminated along with any other factors for any possible errors. The main objective of this framework is to develop the hardware and software of the system to enable remote manipulation of 5-finger movements, which are controlled remotely by any human wearing the artificial intelligent gloves. The distinction of the system is that the angle relationship is obtained with the flexible sensors for detection of the human fingertip angle, and that it can be seen what the robot hand is monitoring simultaneously on the 3D interface. The flexible sensors that can produce as one-way or two-way flexibility are actual detectors whose resistance can be varied by the pressure applied on them. With the aid of these sensors, servo motors can be controlled from 0 degrees to 180 degrees. The relationship between the flexible sensors mounted on the glove and the servo motor angle values. The micro servo motors are the small size and high torques are used for robot hand movements. The torque is 1.8 kilograms centimeters for each servo motor used in the operation, since it is performed only for motion specifications. These torque values are sufficient for the study and can be selected as bigger values for the power required applications. The analog information received from the finger sensors located in the fingers is converted to angle information in the digital form and then sent to remote robot hand through wireless communication modules. The data from the RF transmitter module is sent to the receiver module, where it is decomposed and sent to the servo motors. After converting angle values to character type, different angle values are assigned to the RF transmitter module by combining different ASCII characters from the beginning of the angle values to distinguish the 5 different angle values. After these angle values are discriminated, they are sent to the servo motors. by applying the pulse width modulation technique. This operation is applied to 5 servo motors in the same way, and the angle information is sent to the interface via the serial communication subsystem. The artificial intelligence robotic hand synthesis process will determine the topology and dimensions of a kinematic chain of mechanisms to drive the robot fingers. A dimensional synthesis requires a definition of the topology that should be approximated to human hand structure. In practice, the characteristics of commercial actuators limit the possibilities. The synthesis problem suggests a careful selection of the actuators, sensors, and control mathematical software algorithms. In this application, the flex sensors are used in order to measure the bending of the fingers. So when the sensor is fixed, the resistance across the sensor increases. Therefore, the signals from the sensors are sent to the CPU to process the control, the servo motor. The anthropomorphic robotic hand system determines the shape of an object and selecting the correct method for grabbing a specific object. The autonomy of this sophisticated artificial integrated is achieved through the use of unique control systems that takes input from sensors embedded in the hand to determine the shape of an object, the position of each finger, the grip strength, and the quality of the grip. In this specific application, I use transformation algorithms. These algorithms are tightly constrained parameters defining the length of vectors, their angle tolerance relative to the other vectors, and their distance to other potential vectors, which can drastically change the computation time, accuracy, and usefulness of the current solution.
The goal of a supervised learning algorithm is to find a function that best maps a set of inputs to their correct output. An example would be the classification task, where the input is an image of an animal and the correct output is the type of animal. The motivation for back propagation is to train a multi-layer neural network, such that it can learn the appropriate internal representation to allow it to learn any arbitrary mapping of input to output. The neural network algorithm corresponds to a function which, given a weight, maps an input to an output. The optimization takes as an input a sequence of training examples and produces a sequence of weights starting from some initial weight, usually chosen at random. These weights are computed in turn. First, compute using only 4. The output of the algorithm is then given a new function. The computation is the same in each step. Calculating from is done by considering a variable weight and applying gradient descent to the function to find the minimum starting at. This takes the minimizing weight found by the gradient descent. The learning algorithm can be divided into 2 phases: propagation and weight update. Phase 1 is propagation. Each propagation involves the following steps. 1. Propagation forward through the network to generate the output values. 2. Calculation of the cost. 3. Propagation of the output activations back through the network using the training pattern. Target to generate the deltas, which is the difference between the targeted and actual output values of all output and hidden neurons. There are 2 modes of learning: stochastic and batch. In stochastic learning, each input creates a weight adjustment. In a batch learning, weights are adjusted based on a batch of inputs, accumulating errors over the batch. Stochastic learning introduces noise into the gradient descent process. Using the local gradient calculated from one data point, this reduces the chance of the network getting stuck in local minima. The batch learning typically yields a faster, more stable descent to a local minimum, since each update is performed in the direction of the average error of the batch. A common compromise choice is to mini batches, meaning small batches, and with samples in each batch selected stochastically from the entire data set. Phase 2 is the weight update. For each weight, the following steps should be taken. First, the weight output delta and input activation are multiplied to find the gradient of the weight. 2. The ratio percentage of the weight's gradient is subtracted from the weight. This ratio percentage influences the speed and quality of learning. The greater the ratio, the faster the neuron trains. But the lower the ratio, the more accurate the training is. The sign of the gradient of a weight indicates whether the error varies directly within inversely to the weight.
The example that I illustrate in this video of the multi-layer perceptron has 4 inputs, 3 outputs, and its hidden layers contain 5 hidden units. Since the input layer does not involve any calculations, producing outputs with this network requires implementing the computations for both the hidden and output layers. Thus, the number of layers in the MLP is 2. You need to note that these layers are both fully connected. Every input influences every neuron in the hidden layer, and each of these in turn influences every neuron.
Artificial intelligence has arrived, and it is here to stay. In the short term, artificial intelligence, as primitive as it is currently deployed, will continue to enhance and will augment human productivity. At this point in time, AI, artificial intelligence, robotics, will continue to evolve, and each evolution cycle provides enhanced cognizant capabilities to these robotic systems. The projects illustrated in this video do not pose a challenge to any human being.